Now I'd like to discuss the next section regarding the resonance structure. You learned the process of writing the proper Lewis structure for polyatomic ions and the molecules, and to be extended out to the ionic compounds. The process is it's a bit tedious, but it's doable. You'll have to be very rigorous on the steps and sub-steps that will take to get to the proper valence, proper Lewis structure. Essentially the arrangement of all the valence electrons. Let's take a look at an example of a carbonate. Let's look at the carbonate ion. There will be CO3, have a 2- charge on it. Goes through the motion. Each carbon will have 4 valence electrons. When you have 1, and oxygen you have 6 valence electrons. Now you have 3, and do not forget you have to add 2 valence electrons to account for the charge. So the total number of valence electrons will be 4 plus 12 plus 2. There will be 4. There will be 4. That will be 18, and that will be 2, and this would be total will be 24. 4 plus 18 plus 2 is 24 valence electrons. Next, we'll decide what's the central atom. That will be carbon, because carbon has a lower electronegativity. And you draw the oxygens surrounding the central atom. Now you take 3 single bonds to link those oxygen atoms with the central carbon atom. You use it up about 6 valence electrons. So you have 24, and you subtract 6, you have 18 valence electrons left. Then you satisfy the octet from the outside. And the next step will be checking on the central atom, and you can see central atom when you have 6 valence electron on it. So it will be the best just to take a lone pair that is not shared on the oxygen atom and form a double bond. Now you have all those atoms would have the same octet, 8 valence electrons around it. So kind of everybody's happy, and we bracket up, put it as a -2 charge. However, as you can notice, the double bond is drawn on this particular oxygen, so you cannot argue. We can actually draw it slightly differently. We can draw it on the carbon, and 1, 2, 3, 4, 5, 6, and the other is carbon 1, 2, 3, 4, 5, 6, and the double bond I draw with this oxygen atom. It gives you 2- charge. Same token, you can draw it the other way. So the carbon, oxygen. So now if I over shifting the double bond on this particular oxygen, so if you're looking at it, there are multiple ways of writing the Lewis structure for the same entity, in this case carbonate, polyatomic ion. So which one is correct, which one is not? And this is first to introduce the concept of resonance structures. Resonance structures, as I showed it before for the carbonate, is more than one Lewis structure with the same connections are possible. As you can see from here, the double bonded oxygen can be on this, the top oxygen atom, and it could also be on bottom left, 2 minus, or you can have all this. All these three are called resonance structure for carbonate ion. And a lot of times, actually, people use double arrow to indicate those are resonance structures. So when you actually take a look at the actual molecule, you can take a snapshot on average. The bond arrangement will be the average of all the valence of all the resonance structures. So those structures refer to the resonance structures. So let's reiterate. More than one dot program, the same connections are possible. Those are the ones called the resonance structure. Resonance structure. Use the double arrow to indicate the actual structure will conform to the averages of the solutions. Let's take a look at some example. First example will be ozone. There'll be O3, and as you can tell, that will be 6 times 3, 6 valence electrons. We have 3 of them, and that will be 18 valence electrons. Which one would be the central atom? No choice, but an oxygen. Link those two together, 18 valence electrons. 4 valence electrons gives you 14 valence electrons to operate with. Now we're going from the outside. 6, 1, 2, 3, 4, 5, 6. Those two ends have satisfied the octal rule. Got 2 left. Will be put right in the middle. Right in the middle. But however, and you can see it before check on the central atom, it only has 6 valence electrons, so it's short of 2. So you can actually have that. And this time form a double bond. Okay. However, and this is going to be in resonance form as compared to that structure. So in this case, O3, we have 2 resonance structures. So now you know the whole process. Let's give you some examples to see whether you can solve them or not. The first example will be nitrate ion. Will be NO3 minus. The second one will be the sulfur dioxide. That would be for the molecule, not for polyatomic ions. And the third one would be another polyatomic ion, sulfur sulfate ion. SO4 2 minus, SO4 2 minus. I actually want you to pause here and get a piece of paper out and write on that piece of paper the process of determining the Lewis structure, Write out any possible resonance structures. Okay? So time is up, and let's take a look. Okay, let's take a look. So for the nitrate ion, you will have 5 valence electrons plus 6. This is multiplied by 1. This is 6 valence electrons multiplied by 3 plus 1 because of this negative charge. The total number of electrons, valence electrons, that will be 5, that will be 6, and that will be 24 valence electrons. And then which one should be in the middle? The nitrogen should be in the middle. Link them with the singlets. 24 electrons minus 6 valence electrons, 18 valence electrons. Then the octet, 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. It totally used up. And the octet satisfied, but in the middle it's not satisfied. So the one you will see is the nitrogen. Okay. Oh, what am I doing? Got it wrong. It should be. Oops. So this should be oxygen. However, that oxygen could be in okay. So this, whoops, this is -1. This is -1, and also this. Or, even better, you're going to switch on to, so those are all resonance structures. Or, you can write it N but then you can switch them around. You can have 2 double bonds like that, but however, remember, now you start counting on the central nitrogen atom. Now count how many valence electrons you have. 1 pair, 2 pair, 3 pair, 4 pair, 5 pair. So now you have 10 valence electrons on nitrogen. And that is actually not possible, since nitrogen don't have the third doesn't have the third level. So the this is not allowed. So we end up with 3 resonance structure. Okay, so let's proceed with the rest of the 2. The next one will be SO2, and this is a sulfur. This is a sulfur dioxide. I'm going to jump some steps in terms of writing the Lewis structure. I can tell this is going to be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And you move one of these into form a double bond. And you will have the other way. So this is one of the Lewis structure, and by moving the valence electron around, you can actually have this, and you can go even further. You will have S, okay, and you will say, wait a second, let's take a look at this sulfur. Let's take a look at this sulfur. You actually 1, 2, 3, 4, and 10 valence electrons. That's actually its extended octet. So this is the extended octet. Since sulfur is a group 3 element, which is now has d orbitals, readily for the compound, or readily for the additional valence electron beyond 8 being put on to this element, and the last one just cannot find the right color. And the last one would be, which one would be the last one? The SO4. And forget about that. SO4 2 minus. This is a polyatomic ion, and you can finish it up at home. So with that, let's recap. We have encountered multiple possible Lewis structure for the single compound or polyatomic ion. This is called resonance structure. In later sections, you will becoming amply clear which of those which of those resonance structure will be the most stable one or most desirable one. With that, thank you very much for your attention. Please don't forget to complete the worksheet on the resonance structures. Thank you very much.